Today we're going to talk about a method of estimation for an unknown parameter of a distribution, and that method is called the maximum likelihood estimator. Our first job is to collect data, x1 through xn, which are IID, independent and identically distributed. The independent assumption is critical here. This is typically met in most random samples so long as one observation does not affect the next, and the observations come from the same data generating process or population. Once you collect data, the data has a distribution, and you need to form what's called the likelihood function. The likelihood function represents how likely that event is to occur based on the unknown parameter theta. And it's just the product of the distributions. Your next step is to find the value of theta hat that maximizes that likelihood. After all, that data was observed, so it should be the most likely data to occur for that parameter, okay, for the given parameter. Now, typically, this means setting the derivative of the likelihood function equal to 0 and solving for theta, or the derivative of the log of the likelihood function. These two are equivalent, these two methods, A and B. And you can theoretically prove their equivalence if you like. 95% of the time, people go with option B to maximize the log of the likelihood function. And I typically use log base E for the nice properties of derivatives. So let's work out this process. One important thing to note is that this is the process for the maximum likelihood. Some books even Probability and Statistics by Milton and Arnold mislabels the maximum likelihood. So this is the correct form. So in some books there's a typo, and you can look up this process on the internet or in other textbooks. This is the correct method for maximum likelihood estimation. Now we're going to find the maximum likelihood estimator of P, where the observations are from a binomial distribution with parameter n and p. We've already taken care of step 1, so what we're going to do is we're going to form the likelihood function. This is likelihood function is how likely is it to observe the data for a given value of the unknown parameter p. So this is going to be f of x1 comma p, f of x sub n comma p, that is x sub m. And here these are binomial distributions. So this will be n choose x1 times p to the x1 times 1 minus p to the n minus x1. And this continues m times. So this will be n choose x sub m times p to the x sub m times 1 minus p to the n minus x sub m. And we can simplify this. I'm going to combine some steps. I'm going to combine simplifying, and I'm going to form this L sub p. This is the natural log of the likelihood function of p. And I'm going to write this as ln of n choose x1. And then I'm going to group all these coefficients, n choose x1 through n choose xm. And then I'm going to have an addition. Remember, using the properties of a log, I can change this to be x1 plus x sub m. That's the exponent of p, but I brought it down. Okay. Plus n times m minus x1 minus x sub m times ln of 1 minus p. Now, this is continuous in the parameter p. P represents probability. It can take on anything between 0 and 1. So even though this is a discrete distribution, I can take the derivative of the parameter p. And when I do that, I'm going to do this. The first term is 0. There's nothing involving p here. So the derivative of that first term is 0. The derivative of the second term will be x1 plus x sub m. And I'm going to multiply by 1 over p, so divided by p. The next term is going to be n times m minus x1 minus x sub m divided by 1 minus p. We're going to set that equal to 0, and now we're going to solve for p. So we're going to clear the denominators. x1 plus x sub m times 1 minus p plus p times n times m minus p times x sub 1 plus x sub m equals 0. Now when I do this, I'm going to FOIL, so that times that and that times that. I'm going to get x1 plus x sub m minus p times x sub 1 plus x sub m plus n times m times p And one thing that I want to point out is that I made a tiny mistake. This tiny mistake was in the derivative. So when I took the derivative of that last term, that was the derivative of ln of 1 minus p with respect to p. I multiplied by the derivative of 1 over 1 minus p, but I forgot the chain rule. The derivative of the inside function is 1 minus p. That's a negative. So that changes that to a plus. Okay, so I'm going to have plus p times x1 through x sub m, and that's all going to be set equal to 0. Now the nice thing about this, about catching that mistake, is that this term cancels with this term. And now to solve for the unknown parameter p, all we're going to do is we're going to move this term to the other side and divide by p. Now, I did make an extension of that mistake, is that this term right here is also a negative, and that this term right here is also a negative. Okay. So now if we solve for p, we're going to have x1 through x sub m equals n times m times p. So our estimator that maximizes our probability is going to be x1 through x sub m divided by n times m. Now we could write this just as being x bar over n if we wanted. but this is our maximum likelihood estimator. Okay. Thank you very much. That was an example of maximum likelihood estimation, and it just involves following these steps.